Hello, our presentation is about how thermal mass affects temperature, modeling energy efficient buildings with coolers. Here's our table of contents. We're going to start with physics concepts all the way through the procedure, data analysis, conclusion, and our bibliography.
So kind of from here, we want to focus on a physics concept, which is heat transfer, specific heat capacity, and thermal mass. It's a lot of information, but it kind of just breaks down to the three things at the top: heat transfer, specific heat capacity, and thermal mass. So what is heat transfer? Heat transfer describes how energy flows from the warmer surroundings through the cooler walls into the air in bottles inside. Heat capacity explains why water and soda in the bottles absorb a lot of heat with only a small rise in temperature, while air inside an empty cooler warms up much faster. And then the other key thing is thermal mass, in which a cooler that is full has more mass to store energy, so its temperature changes more slowly than the empty cooler. So why does this matter in everyday lives? Well, with our project, it helps predict how long food and drinks will stay cold and shows why packing a cooler tightly keeps items for colder for longer. So in sustainability terms, this model shows how buildings with good insulation and high thermal mass, aka thick walls, stay comfortable with less heating and air conditioning, which reduces energy use and carbon emissions.
Which brings us to our sustainability aspects, which we see on the right-hand side, reducing heat gain will be equal to saved energy. So cooler drinks have much higher efficiency, which means more overall enjoyment. And energy efficiency is a well-packed cooler stays cold longer, reducing the need for extra mechanical refrigeration or extra ice, which conserve our resources by using less ice, which saves water and reduces electricity required to freeze and transport. And why is this matters? Because small improvements in cooling efficiency would reduce waste and would lower overall energy use and shrink the environmental impact of keeping food and drinks cold. Our observation is that we notice that when we take a cooler on a trip, a cooler that is usually fully packed with cold bottles and cans stays cold much longer than a cooler that is almost empty, even though if we use the same amount of ice, which led us to our question, how does the amount of mass inside a cooler affect how quickly its temperature changes and how long it can keep drinks cold, while also reducing the need for extra ice or extra energy for cooling?
So the first source that we used was from PubMed Central. It stated that in a clinical practice, altercations in temperature can directly impair outcomes associated with anesthesia. So this source, it talked a lot more about temperature control and how it's important, not only for keeping food and drinks cold, but it can also like affect critical medical situations as well. This also showed how important and valuable thermal masses and how important it is to understand the temper change and how it's actually valuable in many different fields. And studying how mass inside a cooler maintains stable temperatures helps explain a lot of broader real world applications, kind of like refrigerating and freezing food or like Uber Eats or DoorDash when they package your food in like thermal or insulated bags. It's kind of like the same thing like that. And it just shows real world applications of heat transfer and thermal regulation.
Our second research source was uh, was about how increasing thermal mass slows temperature changes inside buildings. So this focus more on architecture, but it's the same physics concept that applies to our experiment in coolers that we're gonna explore uh, shortly after. Our third source from PubMed tested out different transport coolers like foam and different contain coolants like ice or frozen water to see how well they maintain a certain temperature. And when they use more frozen bottles, they notice that it can extend the time a cooler stays within the desired temperature. So, if you have more mass or a cooler with more cold bottles, this will keep it cold longer than an emptier one. This led us to our hypothesis, which is the amount of mass inside the cooler will affect how quickly the temperature inside the cooler changes. Our independent variable is the amount of mass inside the cooler, whether it's empty or filled with bottles and cans, and our dependent variable is the temperature inside the cooler over time. Which led us to our prediction that if we fill the cooler with bottles and cans instead of leaving it empty, then the temperature inside the full cooler will increase more slowly and will stay lower than the temperature inside the empty cooler during the same time period. For our procedure design, we used two coolers of the same size and same insulation. We use about 20 bottles and cans of a mixture of water bottles and soda. We use a thermometer to measure the temperature inside the cooler. We use the stopwatch app on the iPhone, and we recorded our temperature on a data sheet using a pen. For our procedure, we basically placed both coolers in the same warm indoor location, so they experience the same similar conditions. And we initially left all bottles and cans at room temperature, so they all start at about the same initial temperature. We packed one cooler with bottles and cans, like the picture to the right, and one we left empty, and we closed the lids. And we then started measuring the temperature. We opened them one at a time and recorded the initial temperature. We closed the lid, and we repeated this every 10 minutes until we reach 120 minutes. After 120 minutes, we gathered our data and we were able to graph them and analyze them. Here are our data. And as we can see from the graph on the right hand side, the temperature of empty cooler rose higher and faster, rose more than the temperature of the full cooler. Basically, the graph shows a steeper curve for the empty cooler and a much flatter curve for the full cooler, meaning that the full cooler has greater thermal mass and higher specific heat capacity inside. So on average, the empty cooler warmed about 3 times faster than the full cooler. This brings us to conclude that the research question showed that increasing the mass inside the cooler slows the rate of temperature change, and our prediction and hypothesis were both supported that the amount of mass inside the cooler affects how quickly the internal temperature changes. Here are our multiple choice questions, and this is our bibliography. Thank you.